Hi, welcome to this session on optimal torque control workflow for permanent magnet synchronous motors. My name is Raghunath and I work with MathFux. I have bachelor's and master's degrees from IIT Madras in electrical engineering, and I have about 17 years of industry experience, primarily automotive, ranging from embedded systems to electromagnetic design for the motors to motor controls. I will be walking you through few workflows to create optimal controls for motors for efficient operation. During this presentation, we will go over a few topics including the ways to characterize a PMSM, usage of the characterization data to define constraint curves, definition of optimal currents, and ways to generate the optimal current maps. Towards the end of the presentation, you will be able to understand how to reduce the time taken to create the optimal reference current maps for the PMSM through MathFux tools. The focus of this presentation is PMSM. There are different design configurations for PMSMs. In this slide, you see different stator and rotor configurations, each suitable for different application. These PMSMs could also be classified into two top-level configurations, those with magnets on the surface of the rotor called SPMSMs and those with embedded magnets called IPMSMs. Each has their own application and advantages. Both the types of motors are useful for automotive applications. IPMSMs are a popular choice for automotive traction applications due to their high power density. For the traction applications, how to choose a motor rating? If we want to design an electric powertrain, we start with considering a drive cycle for a known vehicle configuration. Then, we can derive the torque requirements. The entire set of speed and torque operating points are used to find the points that are most used, such as these. If we do not have optimal operation at these points, and if the motor operates with high losses, the overall vehicle efficiency comes down, resulting in degraded performance. To have optimal operation, it helps to characterize the motor, that is, find the behavior of the motor under different operating conditions such as speed and torque. At the first glance, finding the motor characteristics data also helps us define the speed torque characteristics to check if our operating points are covered by the design or not. Let's look at how we characterize the motor. Now for characterizing the motor, we could choose to work with lumped parameters or nonlinear parameters. What do we mean by nonlinear parameters for a motor? When a motor is operated within the linear region with small values for currents, it will have no change in the characteristics such as inductances. Only when the motor's iron core saturates, the resulting inductance reduces and hence the characteristics depend on the operating currents ID and IQ. At high load conditions or high speed conditions, one or both of D and Q axis currents may have high value, enough to saturate the soft magnetic core in the stator. Lumped parameters would simplify the model and give the advantage of faster simulation. But what if you want your model to behave closer to your actual motor? Then FEA-based PMSM model would be a better choice. This is because instead of having constant parameters for inductances and permanent magnet flux linkage, now your motor has a nonlinear mapping between flux linkage, current and torque. So this will give you a realistic closed loop simulation. If you got your motor from a supplier along with the data sheet, you can pick the critical parameters such as resistance, inductances and the flux PM linkage. If such data sheet is not available, you can go through the parameter estimation workflow to get the data when the motor is available with you. At the end of this activity, we would obtain RS, LD, LQ and flux PM. If we have a motor that we believe works in saturated regions, which is the case for most traction applications, then we can obtain the FEA data, which is composed of inductance maps or flux linkage maps on a grid of ID and IQ. If we are sure that the motor core is not saturating, then we can pick a single value from the uniform inductance maps to assign as lumped parameter value. What if the FEA data is not available? Then we can work with the actual motor and mount it on a dyno to characterize it. That is, we find the impedance maps or flux linkage maps from our test data. At the end of this exercise, we would obtain the resistance along with the inductance maps and flux linkage for the permanent magnet, or resistance and inductance maps along the D and Q axis on a grid of ID and IQ. Let's see the ways to capture the data from the motor dyno now. For characterizing the motor, we can run the motor through different speed and torque operating points. So thereby we can capture IA, IB, VA, VB, theta E, which is the electrical angle, torque and speed. Instead of capturing IA, IB and IC, we capture only IA, IB, assuming that the motor's winding is balanced winding. And we can use Clark and Park transformations to find ID and IQ, VD and VQ. And we can use the standard motor equations given below here to find the flux D and flux Q maps at every operating point, speed and torque. At the end of this exercise, we would have arrived at the following motor characterization data, which is flux linkages in both D and Q directions as maps, 2D maps, on a grid of ID and IQ. Alternatively, we can also run the motor through injected ID and IQ reference currents to observe the achieved speed and supported torque. This eliminates the step where we compute the speed and torque transformations to find ID and IQ, since we already have them upfront. For control purposes, we may not need the rotor position, so that motor characterization data will be at 2D lookup tables based on the ID and IQ operating points. So we only need to spend time to run the motor tests to characterize the motor. These tests could be run with sufficient speed and torque grid resolutions to capture variations in the inductances or flux linkages within these operating regions. We may choose to go with 100 test points with a resolution of 10 speed grid points and 10 torque grid points. If this does not capture the flux linkage variation smoothly, we can add more test points. Once you obtain the flux linkages, you can also define your inductance maps from this data. Now that we have the motor plant model defined, we need to control the motor to be able to run it at a given speed to support the torque demand. Now we'll see how we control the motor. We need to be able to make the motor run at different speeds, supporting different load conditions. A preferred way is to use a field-oriented control as given in the picture here, whereas the inputs are D and Q axis current references to support the motor's operating speed and torque. A set of PI controllers could be implemented to track the reference currents. To be able to run this control, we need to understand the motor's behavior, or in other words, motor's characteristics data, which we saw in the previous slides. Now that we have this motor's characteristics data, we need to control the motors to operate optimally. We see two PI controllers for the current control in the green box and one PI controller for the speed control. The torque reference as obtained from this PI controller and operating speed are used to find the reference currents. For the control implementation, motor parameters are provided at two locations in the figure: the optimal reference current generator and the plant for the motor. For the right PID controller, the system currents will follow the reference currents, and so it is important to correctly define the reference currents so that the system can operate with the lowest amount of inputs. So how do we define the optimal currents now? What is optimal about this? This could be the current that results in the highest torque or highest efficiency or any system level behavior for the lowest amount of current. For example, a motor may generate the same torque for different input currents, but there exists the lowest amount of current that can still produce a required torque. In this case, the motor current control happens in the D and Q plane. So we have two different currents in each direction, one taking care of the torque production and other taking care of opposing the rotor field. On the figure shown here, the red line has all the points on the IDEQ plane to give the same torque output for an example motor. As you can see, one point gives the lowest current magnitude for the same output torque. That point can be noticed as a third point, which goes along the dotted line in this figure. Now, how do we find the optimal reference currents for controlling the motor? If we want to find optimal reference currents by directly mounting on a dyno and then trying to find the best ID IQ for every speed, starting from 0 to the maximum speed, and for every torque from 0 torque to the peak torque, randomly searching for the best ID IQ for every speed and torque operating point, it will take a long time even for a single operating point. Creating a map of the reference currents for the entire operating region is a few weeks effort. Is there any easier way out? If the motor's characteristic data is available, we can generate the optimal reference currents very quickly through the solutions offered by MathWorks. Whenever required, we can quickly check around the given reference points to see if there are small corrections. These reference currents can be created from motor control Blockset's APIs or from model-based calibrations APIs and the GUI workflows by defining constraints and the cost functions. Model-based calibration is a generalized optimization toolbox allowing you to follow the same workflow defining constraints and cost functions for any motor topology. Motor control Blocksets implements the turnkey functionality in an API or a block. So if a motor topology changes, for example from PMSM to SYNRM or a PMA SYNRM, then appropriate block need to be selected. In this presentation, we will be focusing on motor control Blockset. And this is a block that motor control Blockset offers, which will be providing the features to create optimal reference current lookup tables. Before we directly compute the optimal currents, let us step back and understand the fundamentals, and then we move to finding the optimal reference currents from there. The curves you see on the screen are called constraint curves of a PMSM. These curves visually and mathematically define the valid operating regions of the motor depending on the operating conditions. These curves help us find the possible currents and help us pick the best IDIQ reference current points based on the conditions we impose. A simple script can be used to generate these curves. We will understand each curve in the next few slides and then look at how these curves help us derive the optimal currents. Let's begin with the constraint curves one by one, starting with current limit circle. This is a simple curve, a circle representing the limit of current from the source, drawn on DQ plane of reference, which is a rotating frame of reference. Operating current points given by ID and IQ lying inside or on the current limit circle represent valid points, meaning that the points satisfies the current constraint. Let's look at the constant torque curve now. This is represented by a red hyperbola in the figure. The empirical expression for the torque as a function of lumped motor parameters is given in the bullet point here. When IQ is written as a function of ID and a given torque, we will be able to draw this curve. When the torque increases, the curve shifts upwards as shown in the figure here. Now let's pick one torque curve and notice that we marked 2 points on the curve. Both the points have different ID and IQ values but have same torque value. By definition, all the points of a constant torque curve have the same torque output for the given motor parameters. Now let us pick one particular torque curve and assume that we have limited the current to the system that can give only this torque. Let us draw the current limit circle for this new current. We notice that the new current limit circle and the corresponding constant torque curve intersect at a single point tangentially. With this information, let us look at the next curve, MTPA curve. Assume that we draw multiple constant torque curves and corresponding current limit circles that touch these torque curves tangentially. The locus of all the tangential intersection points is called MTPA curve, also known as maximum torque per ampere curve. This MTPA curve defines the lowest amount of current in both D and Q axis required to produce the torque demanded, and this represents an efficient operation till the base speed. The next curve we learn about is called voltage limit curve. This is influenced by both speed and voltage of the system. The system voltage Vmax is defined as VDC by square root 3 for a space vector PWM, whereas it is VDC by 2 for sine PWM. Empirical equation for the voltage limit curve for lumped parameter motor model is given here. Any IDIQ point inside or on the voltage limit curve is a valid point that satisfies the voltage constraint for the given speed. When the speed increases, the voltage limit curve shrinks, which means less region is available for the points to satisfy the constraints. Now there is an overlapping region available for the voltage limit curve and current limit circle, where these points from this overlapping region satisfy both voltage limit and current limit. The bright red line segment inside the overlapping region is a segment of the constant torque curve, whereas the points on this segment represent the set of points that satisfy all the three conditions: the current limit, voltage limit, and the torque demand. Now we will look at how different motor parameters affect the shape and placement of the voltage limit curve. When the system's resistance is increased, we see that the voltage limit curve shifts and tilts downwards. When the system's saliency is increased, we see that the voltage limit curve gets flattened out. You can have a better look at these curve changes when you look at the presentation. Here we look at the steps to find the optimal different current maps. First, we'll try to find the motor's characterization data, and then we draw the constraint curves for these operating conditions that are speed and torque. Then we identify the conditions that are required for optimality. Then we try to identify the limiting cases. Then we try to find the best possible torque to be given out. Then we identify the intersection points of these required curves. The IDIQ point that is at the intersection of these curves is logged into the lookup table corresponding to the speed and torque that is used. Now we know what the constraint curves are and how they change. How to use these curves? Let's take an example motor whose parameters are picked from the default mask values of the block LUT-based PMSM Control Reference. The resistance is updated to 10% of the default value so that the voltage limit curve appears horizontal. With these parameters, the rated torque comes to around 0.28 Nm, while the rated speed is around 4800 rpm and the maximum speed is around 6600 rpm. We used lumped parameter model for the motor so that our computations are faster. The curves look like the ones that we saw before. Let's now consider a case where we need to find the optimal different currents for an operation when the motor's demanded torque is less than the maximum, and for the given operating speed, the motor's voltage constraint is still satisfied. We notice that two plots on the left. The top left figure shows the torque speed characteristic of the motor in solid thin blue line. We pick an operating point 0.1 Nm and 5000 rpm, which is well within the envelope of the curve at the original current limit of the system. The dotted thick blue line represents the speed torque characteristic of the motor when the motor is operated at a reduced current limit to reach the demanded torque. This curve is plotted to see what the operating currents are for the motor under the speed torque operating conditions. The bottom left figure shows the currents ID and IQ drawn with respect to the speed corresponding to the speed torque envelope points. The thin solid line represents ID when shown in black, IQ when shown in blue for the original current limit for the system. The thick dotted lines represent ID when shown in green, IQ when shown in magenta. When we plot the constraint curves for the load torque and operating speed, we get this figure on the right. Now, we will use the areas to represent valid operating points of individual constraints. Green represents area of points that satisfy current constraints. Blue represents area of points that satisfy voltage constraints for the operating speed. Bright red line represents the points that satisfy the torque demand while also satisfying the current and voltage constraints. Notice that in this segment, the points 2 and 3 represent the ends of the line segment that falls within the overlapping region of the blue and green areas. The thick gray circle represents the current limit circle that intersect the constant torque curve tangentially. Point 1 is the intersection point of reduced current limit curve and constant torque curve. This is a point ID and IQ that represents the lowest amount of currents that can be provided to the system to meet the demanded torque, while also meeting the operating speed requirements. When we zoom in on the regions of this curve, we notice that the point 1 has the ID-IQ coordinates that match with the ID and IQ values marked on the figure at the bottom left of the screen. As you can notice, this point happens to be the point on the MTPA curve representing the MTPA operation. The optimal operating point can be identified by the intersection of the constant torque curve and MTPA curve. Doing this analysis manually seems intuitive, but we need to be able to do this for many points and also quickly. Doing this computation mathematically for non-linear motor parameters is tricky. But this is also not the only possible case of operation. We need to also consider other operating points too, such as the next one where the operating speed is higher than this case, such as the voltage constraints dominate the operating current selection. Let's come to the case where we operate the motor within the same torque demand, but the operating speed is higher, 6000 rpm. For this motor at 6000 rpm, the voltage limit is reached when we operate on MTPA path. This requires field weakening operation, that is, we have to provide higher ID on the negative direction to support opposing the rotor's magnetic field. The figures on the left have the same meaning as we discussed in the earlier slide. Now we can see that the operating points 0.1 Nm and 6000 rpm fall within the speed torque envelope of the motor within the maximum current limit. When we draw the constraint curves for the operating point, we get the figure on the right, and then we can color the areas to highlight the regions that satisfy the constraints. Bright red line segment represents the points that satisfy current limit, satisfy the voltage limit at a given speed, and also meet the torque demand. The points 1 and 2 represent the ends of the line segment. The thick gray circle represents the minimum current that can meet bright red line segment. This corresponds to point 1. When we zoom in to the area of intersection, we see that this point is the intersection of constant torque curve and voltage limit curve. The IDIQ marked from this intersection also match with the points marked on the bottom left curve. Now, finding this point appears reasonably fine for lumped parameter model because of the uniform shape of the curves. For a motor with nonlinear parameters, the curves are not uniform, they have deviations. Finding intersections through mathematical means is a tricky process. Did we cover all the points of operation for MTPA and field weakening? Not yet. Now, let's look at a case where the demanded torque is higher than the maximum torque motor can provide. When the motor's operating speed makes the voltage constraint limit the choice of operating points, that means the motor will be operating in field weakening region. We pick a speed of 6575 rpm for this case. In the top left figure, we see that the demanded torque 0.1 Nm is represented by the magenta star, and this point is beyond the speed torque envelope of the motor. The same meaning for the curves hold true from our last discussion. When we draw the constraint curves for the motor for this operating point, we arrive at the figure on the right. When we see the overlapping regions of blue and green areas, we notice that there is no intersection with a constant torque curve. This means that at the given speed, the motor will not be able to support the requested torque. We know that when the torque reduces, the constant torque curve shifts downwards. We can reduce the possible torque value till such a level that the constant torque curve of the reduced torque intersects the overlapping region of current limit circle and voltage limit curve. Such maximum supported torque curve goes through the point 1 of the intersection area of the figure. This curve represents the maximum system current being used, as shown by the gray circle. When we zoom into this zone, we can see that the point picked has ID and IQ coordinates that match with the values on the bottom left figure. This represents a special case where the torque output is reduced to a possible value and the IDIQ corresponding to the reduced torque are provided. An alternate way is to provide a solution where instead of reducing the torque to maximum possible torque at this speed, we can support the torque but provide an IDIQ corresponding to a reduced speed. But in a physical system such as a vehicle, the speed will not be changing instantaneously. So, providing this output will result in IDIQ values corresponding to a speed which is different from the motor's operating speed. Hence, we pick the option of maintaining the speed while reducing the supported torque to a possible value for the corresponding speed. We see that the optimal operating point is given by the intersection of current limit circle and voltage limit curve. Now we will look at a different curve from the constraint curves called MTPV curve, that is maximum torque per voltage curve. This curve gives locus of all the points IDIQ which provides maximum torque for a given voltage constraint based on the operating voltage and speed. This region of operation is also called deep field weakening region. Not all the motors are designed to have MTPV region of operation. These are the motors that are specifically designed to have either weaker magnets or high current limits. These types of motors theoretically have infinite maximum speed, only limited by mechanical limits or frictional torque limits or thermal limits. We will look at these special motors controls within this MTPV region of operation. When we look at the figure on the right, we notice that we have multiple voltage limit curves and multiple constant torque curves. We pick the speed and torque values such that each constant torque curve intersects a voltage limit curve tangentially. The size of the current limit circle does not matter here since these curves are drawn only for demonstration for an example motor. The tangential intersection means that when the motor is operated at this speed, as long as the motor's current limit supports, the voltage limit curve will have single point that supports the demanded torque. That means this is the maximum torque that can be supported with a given voltage constraint at the operating speed. When we join all the tangential points, we obtain the magenta curve, which is what we call as MTPV curve. The empirical equation for the MTPV curve, even for the lumped parameter based model, is a complex expression. What you see is an equation in terms of VD and VQ, and it still needs to be expanded into ID and IQ terms to form an actual MTPV curve. We will now modify our example motor to have higher current limit, that is 40 amperes. When we do this, the resulting motor will have a possible MTPV operating region. With these parameters, the motor's speed torque characteristics also change. Notice that the maximum speed of this motor is very high, as we said before. Also, for this case, we use lumped parameter model for the motor. That is to simplify plotting of the curves and calculations. Now we will look at a case where the motor is operating at a speed with a torque demand which is lower than the maximum possible torque at that speed. The definition of the curves from the left two figures is same as before. We consider a speed of 20,000 rpm and a torque of 0.25 Newton meter. When we draw the constraint curves, we arrive at the figure on the right. Notice that the voltage constraint curve is smaller than before because it is drawn at higher speed than before. Also notice that the center of this ellipse is within this current limit circle. This is a special characteristic of the motors with MTPV region of operation. When we draw the blue and green regions representing the current limit and voltage limit constraints, we see that the voltage limit region almost fits within the current limit circle. For a slightly lower speeds, the voltage limit circle may have slightly larger size and it may extend outwards too. But for this case, we notice that the bright red line represents the set of all IDIQ points which satisfy current limits, voltage limit for the speed, and also meets the demanded torque. The points 1 and 2 represent the ends of the bright red line segment. We notice that the point 1 has the lowest magnitude of current which can satisfy the constraints while meeting the operating conditions. When we see the zoomed in portion of the intersection, we see that the resulting optimal operating point is given by the intersection of the constant torque curve and the voltage limit curve. There can also be a case where the demanded torque is more than the possible torque at that speed. When we pick 0.25 Newton meter at 30,000 rpm as an operating condition, we see that this point falls outside the speed torque characteristic of the motor. When we plot the constraint curves, we see that the figure on the right, and we notice that the voltage limit ellipse is completely inside the current limit circle, and this is smaller than the one we saw for the 20,000 rpm on the last slide. Also note that the constant torque curve does not go through the intersection region, meaning that the demanded torque is not possible. The highest possible torque is a value that results in a constant torque curve that tangentially intersects the voltage limit curve. This happens to be a point where MTPV curve cuts the voltage limit curve as shown in the figure. We go through a complete grid of speed and torque points to find optimal currents, ID and IQ for each point. For computing the ID and IQ for each operating conditions, we need to go through all the cases that we have seen before and select the best operating region, MTPA or field victim or MTPV. The IDIQ optimal points that are computed can be plotted on an IDIQ plane as shown in the figure on the right. The figure here represents the case where the motor does not have MTPV region, and this figure represents the case where the motor has MTPV region. We will get to the explanation about this figure in the coming slides. The complexity we saw for computing the optimal currents is for the lumped parameter model only. When it comes to the case of nonlinear parameters for the motor, this becomes even more complicated. How to simplify this? We can use the APIs provided by motor control Blockset. The APIs go through the cases for every operating point and rigorously compute the optimal points based on the available motor characterization data. As we noted earlier, if an engineer wants to create these lookup tables from manual calibration workflow by going through IDIQ space for every speed torque operating point, it would take few weeks. With the help of APIs from motor control Blockset, this operation can be completed in a matter of seconds, and all such points for a grid of speed and torque operating points can be computed on the host PC. Let us look at how to use the APIs. The function MCBGenerateTables can be used from MATLAB command prompt to generate the lookup tables. The PMSM is a structure type variable with all the required fields. The nonlinear motor parameters are also provided as fields to this structure in an appropriate format. To simplify this process, motor control Blockset also has a block called LUT-based PMSM Control Reference, which accepts the inputs in a format easily accessible to the users. The plotting options tab on the block mask also provides a way to generate the IDIQ lookup tables by clicking the highlighted buttons from the figure on the right. When we look at the IPMSM's possible input fields under the option Motor Parameter Input Method, we see that lumped parameters can be provided when the first option is selected. These parameters could come from the datasheets or parameter estimation workflows. The next two options under the motor parameters input method helps us provide nonlinear maps of the motor characteristic data in the form of flux linkages in DQ axis directions or impedance maps and PM flux linkages. This set of data can be obtained from FEI simulations or from the dyno tests as we saw before. If you have used MCB generate tables or any other approach to create the lookup tables for ID and IQ on a grid of torque and speed, the last option under the motor parameter input method helps you provide this as a direct input. When the motor is operated with a fixed system voltage, there is going to be no effect on the IDIQ lookup tables since the voltage limit curves at any given speed only depend on the speed. But in practical applications such as automotive traction applications, the battery voltages are prone to change. When the system voltage changes, we need to account for the change of shape of voltage ellipse with respect to the updated voltage when drawing the constraint curves and while computing the intersection of the curves for computing the IDIQ lookup tables. For a fixed operating voltage of a system, we can pick the first option under the option VDC input method and provide the fixed voltage as a mask input value. When the voltage of the system is a variable during operation, there are two ways in which it can be handled. For every value of the voltage on the voltage grid, we can create another option for the IDIQs for a given operating point's torque and speed. This results in a 3D lookup table with breakpoint vectors, torque, speed and voltage. To pick this option, we can select the second option under the VDC input methods to provide 3D lookup tables for ID and IQ by providing VDC grid in addition to torque and speed grids. There is also another way to handle the variable voltage in a simpler manner when the phase resistance is reasonably low. This includes an internal algorithm to consider the 2D lookup tables of ID and IQ at a rated voltage, and it scales the speed to a new value called scaled omega. For systems with relatively small phase resistances such as automotive applications, this results in outputs that are very close to the 3D lookup tables outputs, and this also makes the memory footprint of the block smaller. This option can be chosen by selecting the third option from the choices for VDC input method. We will look at the IDIQ lookup tables from the figures generated from the block. The figures on the right are surface plots of the ID and IQ lookup tables on a grid of speed and torque. When the same points are plotted on the IDQ plane, we get the figure on the left. Each black dot on the figure represents an optimal difference ID and IQ for a certain speed and torque operating point. The pale blue ellipse segments represent the constant speed curves, representing the segments of voltage limit curves at different speeds. All the points along any of this curve represents the same speed, but it changes the torque operating point. The pale red hyperbola segments on the figure represents constant torque curves for different torques. All points along any of this curve segment maintains the same torque, but it changes speed operating points. You can click on the black dots to create the data tip showing the details of the optimal currents and the corresponding operating speed and torque. These data tips, when created from the direction along the constant speed lines, can be dragged along the constant speed curve. Also, if these data tips are created from a direction along the constant torque line, the data tip can be dragged along the constant torque curve. Any speed and torque operating point within this grid of speed torque breakpoints will use the neighboring 4 points and interpolates among them. So that completes the implementation. Let's look at a small demo of how the LUT-based block can be used. Now we have this block here and we have this default parameters where the motor topology can be surface PMSM or interior PMSM. If we pick the surface PMSM, we have an option to pick different field weakening methods. VCLMT stands for voltage current limited max torque. CCCP stands for constant current, constant power. CVCP stands for constant voltage, constant power. And interior PMSM selection would give us different options for the motor input parameter methods, which changes from linear model to DQ flux linkage LUTs to LDLQ and flux PM LUTs, and the IDIQ LUTs as the pre-computed values. If we select DQ flux linkage LUTs, there are ways in which we can provide flux D, flux Q on a grid of ID and IQ. If we select LDLQ and flux PM LUTs, we can still give LDLQ and flux PM on a grid of ID and IQ. As we said, if we say ID and IQ LUTs are pre-computed, we can also directly give this ID and IQ on a grid of torque and speed. Let's go to the lump parameters for the ease of computation, and let's also look at how the 3D how the voltage variations can be included. The default option is specify via dialog, which will say that input DC voltage can be provided on the mask. And if we say the 3D lookup tables, which is voltage slice based, which will produce different slices for the 3D lookup tables for every voltage that we provide here. And any intermediate voltage will be interpolated between these two slices for the voltage variations. And if we say a scaled omega based, we will also have the input port for the VDC, but we will also have single reference voltage in which the 2D lookup table is computed, and based on the input voltage, the omega value of the block input will be scaled to obtain the required value for the omega of the lookup table at the base VDC. Now that we have these 2D lookup tables, we will go to the plotting options. We can also compute and see certain motor parameters such as rated torque, rated speed, max speed, and other characteristics. We will see the constraint curves of this motor. We can directly plot constraint curves, and we can see these constraint curves here. The default orientation shown is the second quadrant. As you see, the tilt of this ellipse is because of this higher resistance of this motor, in this case 0.36 ohms. And we can also define custom motor speed and torque at which the constraint curves can be plotted. And we can also enable plotting the drive characteristics. I can go to the constraint curve plot, which will produce two plots. One plot will be the constraint curves, and what you see as a possible control trajectory is the ID and IQ corresponding to the torque speed envelope of these motors. It will also draw the speed torque characteristics and the IDIQ corresponding to that speed torque characteristics, and the peak power and the power versus speed and current versus speed. If you were to use this motor for a short term rating, let's see this motor's rated current is 7.1 and you want to operate this motor at say 10 amperes for a shorter duration. We want to find out how this motor behaves and how the drive characteristics change, whether we will go to 10 Newton meter or only slight increment in the peak torque. We can also enable this value and say this. The constraint curves are similar as before. What we end up here is this. The solid line represents the speed torque characteristics with the rated currents, and the dashed dot line represents the speed torque characteristics with the increased current, the elevated current. Also likewise, we also see the IDIQ for the rated currents and also the elevated currents. So one more thing that I want to demonstrate here is, again within the same options, we can also compute and plot IDIQ LUTs. Depending on the default grid or depending on if you are creating your own custom grid and high density points, number of grid points, this will take longer or shorter. To avoid computing the IDIQ lookup tables each time a simulation is run, the generated IDIQ lookup tables can be saved using the checkbox next to the button to generate the IDIQ lookup tables. This action creates the time-stamped MAT file in the current working directory with a default variable name. For subsequent simulations, this MAT file can be loaded and the block can have the IDIQ lookup tables provided through the loaded variable. The block LUT-based PMSM Control Reference can be used to simulate the controller in addition to just being able to generate the IDEQ reference LUTs. Now this block fits the entire control schematic to create the reference currents. We have also created an example demonstrating the use of the block LUT-based PMSM Control Reference in a motor control simulation. The same block can be used with code generation model too. And the provided example is a simulation only model with no hardware configuration associated with it. This model allows changing the system voltage and also supports nonlinear plant models through the radio selection at the top left. The operating speed and torque can be changed through the dials provided on the model to allow the simulation of different operating conditions as long as the picked operating conditions are within the possible speed torque envelope. Here you can see the screen grab of running the example. So in conclusion, what we have seen is how to characterize the PMSMs. We learned about the constraint curves of the PMSM, how to use the PMSM constraint curves to find optimal currents. We have also seen the generation of optimal reference currents simplified by the usage of the block. And we have also seen how to use optimal currents in real life using the example that is already shipped. Thank you so much.